Welcome back to another episode of Speech Processing. In this episode, we will look at basic ASR applications. So let's do that. Why would you want to do that? Well, of course, just to have a transcript of your audio is useful. Also, to get a forced alignment text grid, like in Prep, for example, to be able to look at segments, that is phones, sounds aligned. And there's some other things that we will look at. And I'm calling this kind of basic because we'll look at some more advanced stuff later. One thing is to do speaker ID and verification, sometimes called speaker biometrics. Simply identify who is speaking and is the speaker who they claim to be, right? Identification and verification respectively. And you can have paralinguistic features like accent and gender and age, emotion, physiological characteristics. The basic idea is to have a closed set of speakers, perhaps at your company or some type of organization where you have a set of speakers and who you want to grant access to or deny access to. And you record each person requesting access just by saying something. And then you compare the utterances of somebody who comes to gain access to the models of the already enrolled speakers. And you determine the best matching speaker. So in the top right of this slide, we see speech coming in and we do some feature extraction, like maybe getting some C's out. And then in the back end, you have a classification machine learning model that you compare the incoming audio to, and you make a decision. Okay. Also, another application of ASR is to do language ID and dialect ID. So I don't know if you ever have seen some of these games where you can listen to some speech and try and guess what the language is. Here are 6 languages. Take a listen. See if you can guess what these are.
திங்கட்கிழமை, செவ்வாய்க்கிழமை, புதன்கிழமை, வியாழக்கிழமை, வெள்ளி.
Mi última comida era 2 huevos.
比较干燥的，冬天冷，夏天热的。
월, 화, 수, 목, 금.
मैं भारत हैदराबाद में रहता था.
Anyway, let me jump to the next slide just real quick so you can see what those were. That's what we just heard. I don't know if you recognize any of them. Maybe the Spanish, those who speak Spanish probably recognize that, or but the others were different languages. Here's kind of the same idea. Here's a fun game. I have links here to a couple games. Let's just go with the beginner here and play a little bit here. Let me zoom in a tad bit on this. Let me play this.
Принимая во внимание, что признание достоинства, присущего всем членам человеческой семьи и равных и неотъемлемых правах является основой свободы.
I'm going to guess Russian, and I got it correct.
Whereas recognition of...
Well, that is English, obviously.
原爆投下以来の2週間ほどで
I'm going to guess Japanese on that. Yep.
王振亚，弟王，自去年7月1号在看。
I think I heard.
Katika taarifa iliyotolewa na msemaji wa Bwana Ban ilieleza kwamba waasi wa zamani wa Kiislamu wa serikali walikabiliana na vikosi cha kulinda.
I wasn't sure about that one, but I didn't think it was Hindi nor French. Anyway, I'll stop there. So that's fun. Here's another one, kind of the same idea. I'll let you look at that. And so perhaps doing that could skip the step on the phone where it says, para español oprime dos. If the person's just talking, just hey, they just start talking and the computer system can recognize the language, they can just direct the call to the right operator who speaks that language. Also, this could be useful in emergency call centers like 911 or 999 if you're in the UK, right? Where in big cities with a lot of immigrants, a person who's in distress and panicking or stressed out may have a hard time using their second language, English, for example, in the US or the UK. And so being able to detect language in that situation could be useful as well. Department of Defense, Signal Intelligence. There's other reasons you'd want to detect language. And this has been extremely vital, so much so that the National Institute of Standards and Technology has hosted competitions for the last couple decades where teams are given 3 seconds or 10 seconds or 30 seconds of audio, and they create a system that is able to, that the competition is to create a system that can identify correctly many examples of different languages, audio from different languages with those varying lengths of time there. Okay. So the main approaches are some baseline, just simply always guess the most common language in the environment. In the US, it'd probably be English, right? Another one is acoustic analysis only, where you train classifiers based on spectral information like MFCC vectors, right? Numbers. But a better one is to also add linguistic information like phonotactics, like the phonotactics of a language are what sounds can go together in a certain language. So for example, in Spanish, you cannot start a word with S followed by a consonant in the same syllable. That's why a lot of loan words from English and Spanish that start with S, some other consonant like special, stress, Smith, often come out as estrés, right? Especial, those are cognates, but Smith, Jose Smith, Joseph Smith in Spanish. Anyway, phonotactics. You can also do broad class phonotactics like, fricatives go here and then stops and then nasals, that type of thing. Phone duration, as well as the amount of silence, as well as filled pauses, right? In English, our filled pauses are usually or So like I'm going to the store and I need to get some stuff. That's our filled pause sound. In Spanish, it's usually like or este sometimes. Voy al mercado, tengo que comprar leche or whatever. In Danish, I think it's a front mid vowel like I understand that from my Danish teacher. And prosody, which is difficult and less effective. So the idea here is that we have, speech data sets. We do feature extraction, and we go through this process, and we come out with a classifier score. We score the different languages, and the top score, right, is the one you propose as the recommended language or the identified language. Here's a comic on the left-hand side of the slide, a comic from 2005 when they were looking for Osama bin Laden, right? Kind of a funny thing where calls that are leaving between the U.S. and outside the U.S. are recorded and monitored for security purposes. And but the ability to actually monitor all those different languages is onerous and a big task. And so being able to simply identify the language being spoken so that it can be routed to some agent that knows that language to just listen in or, in the effort of trying to catch terrorist or nefarious phone calls from going from the U.S. out or in. On the right-hand side of the slide, we have the NSA facility near the point of the mountain here in Utah that stores all sorts of data, including speech data. Typical approaches include creating a phone recognizer to produce the most likely sequence of phones or phonemes. So for each language, you build statistics based on every sequence of N phones. So for example, you may end up knowing that to go together 100 times in this language, but occurs only 5 times, and that can be useful for the application. And then you assign a score based on stats to the output of the recognizer. So we have incoming speech here. Let me remove myself for a second. Incoming speech, right, goes through an acoustic preprocessing, and it goes through the English phone recognizer. It comes up with these, and then we're trying to guess whether it's Farsi, French, or Tamil. And it goes through those, and we end up with a score for each of those. And we also can put it through a Japanese phone recognizer and say, how close is that? And put that into these models of the 3 languages we're trying to guess. Same thing with, say, a Spanish phone recognizer. So we can actually try and guess a language that we don't have a phone model for and combine and pick the max, and that spits out the hypothesized language. Okay, so you pick the language with the highest score. Another approach is to even break it down more and have more models. So here in this diagram, we have input speech right here coming from the left, right? And then we have the acoustic preprocessing. And then we have one model for English for male speakers. Then we have another model for gender independent English speakers, and then a third model for female English speakers there. And we pass that into the models for the various languages we're trying to guess. Anyway, you can see that this can get insanely complex very quickly. When you're trying to guess 10 to 12 languages per gender, per recognizer, right, you're going to have a lot of models. It's going to exponentially grow. So it can get complex trying to figure out what language is being spoken. BYU had a language recognition evaluation system based on Sphinx 4, which is an ASR model, ASR system, right? And it segments phone call audio and returns phonetic data. And it sends the time slices to Pratt to do further processing of acoustic and phonetic features. So in addition to the acoustic features that came out of Sphinx, getting like linguistic features with Pratt, and converting the phones and the acoustic phonetic features to statistical features that can be used to train a classifier, machine learning classifier. And so the basic idea is we have a phone call, comes into Sphinx, sends over time slices to Pratt, do some scripting in Pratt, get some acoustic features and phonemes coming out of here, out of the recognizer, the ASR model. And we have some featured definitions here created by linguists that go into a classifier, a maximum entropy classifier that predicts the language. And so linguistic students looked at sounds, like on the top right of this screen here, and they looked at the acoustics of the sounds and marked different aspects. So we can see here on the bottom right of the screen, what we have here is an XML file, right? We have the average F1 across a 111 millisecond slice of sound. And we have the average F1 right there, the average F2, the average F3, 4, and 5. And then we have the F0 beginning and the F0 at the end of that time slice, that 111 milliseconds. F0 is the fundamental frequency or the pitch. And so you can see that there's a rising pitch. And so this is going from a low fundamental frequency of a score of 2 up to 12. And so this seems to be a tonal language just based on that fundamental frequency shift from low to high across this 111 milliseconds. So yeah, getting more linguistic features is useful to creating a better system for recognizing languages. And here's the basic BYU approach. So instead of phonemes or phonetic classes, they had classes like fricatives and closure and voiced, sound here. And they created this n-gram model, this n-gram language model based on the classes to constrain the recognizer. Okay. There are 3 SR components, right? The acoustic model, the phonotactic language model, that is like this stuff, classes of sounds, and the pronunciation dictionary. So BYU's NIST language recognition evaluation results were good. They did best with English. You can see in the top right of the screen. They did best with English. The cost, the lower the cost, the better. So a perfect system would have a cost of 0. And a cost is simply the weighted average of false negatives and false positives. So you can see in English, we got 46 hits correct, 9 misses, and 3 false alarms. That is, I thought it was English, but it wasn't. With a total cost of 0.082. That's the lowest one. The highest cost language was Korean with the highest, the cost of 0.221 there. And for whatever reason, if it wasn't sure, it would guess Korean. And there's a study that showed that this is also the case with humans, that for some reason humans had a preference to guess Korean if they didn't know what the language was. So it's kind of interesting that it kind of follows what humans do. The system followed what humans do and it wasn't sure. So another application of ASR is speech activity detection. Okay, so detecting the transition between silence and noise and speech, right? 3 things: silence or background noise or actual human speech, right? This can be useful for voice assistance, right? It allows it to wake up. I can save bandwidth for not having to send silence to some system to process silence, right? This can be useful for, audio conference, like conference calls or echo cancellation. Telemarketers, right, use this. You'll likely, if you ever answer a phone call from a number you don't recognize, you say hello, and it takes a second or two for someone to say, hello, I'm here representing whatever. It's this system happening. They're waiting for someone to actually create human speech before it gets assigned to an operator or an agent, because there are likely more numbers that they call than agents available, right? So that is another application of ASR systems. And also word spotting, being able to spot specific words where you're scanning the speech signal and listening or looking for a small set of expected words, and ignore everything else, right? That's what the hot word or the keyword for voice assistance is, like, Alexa, what time is it? Or hey Siri type of things, or hey Google, right? Listening for those keywords. They're using this technology of using ASR and then listening for certain words. It can be used for, command and control for a limited vocabulary. We had a student create a drone and control a drone with speech using specific flight commands, like, go forward, go right, that type of stuff, where he was controlling the drone. We had another student control a camera, a digital SLR camera with a voice ASR system that he built in this class. This can be used obviously for detection of suspicious keywords in phone calls. Like I mentioned in the past, phone calls between the U.S. and outside the U.S. Are monitored, recorded, and eventually listened to or analyzed. And so having software that can automate this and make the analysis much quicker is important. And pulling out specific or specific suspicious keywords is important. Also, here's an example of a government research project that was developing agile and robust speech recognition technology that can be rapidly applied to any human language in order to provide effective search capability for analysts to efficiently process massive amounts of real world recorded speech. So there's an example of it. Another application of ASR is speaker diarization or source separation. This is the idea when you have one recording with multiple speakers in it, and you want to kind of pull out the speech of this speaker one, and then have in one file have the speakers two speech kind of pulled out into its own little separate file. Speaker three, if there's a third speaker, right? So it combines two processes here. It combines speaker segmentation. It finds speaker change points in the audio system, or the audio stream, that is, the stream of signals, and then speaker clustering to group together all those speech segments based on the speaker characteristics, and to output audio into separate tracks or separate files, usually at least at the utterance level with timestamps. So here's a demo of speaker diarization or source separation using SpeechBrain. Let me get out here, and if I go to here, so I'm going to use SpeechBrain. Let me zoom in a bit here. Well, let me actually show you the audio I'm going to use. Let me go over this screen and grab the audio, bring over Audacity to here. So here is a little bit of audio that my daughter and I created. Listen to it. My name is Earl Brown, and I teach linguistics at Brigham Young University.
I like to eat art.
So this is like the worst case scenario when two speakers are speaking at the very same time for a long time, and trying to have the system pull out the two speakers, voices from each other and create two different audio tracks is what this does. You can also just have turns, right? Just one turn after another. But let me show you how this can work. So I'm just going to use a Google Colab here. SpeechBrain, I installed SpeechBrain right there. There's the audio I just played. That's the WAV file right there. And then if I run this may take up to 30 seconds to do. It's in Python. This is Python code you may recognize. I'm using, while it's working, we can talk about this model right here. This model I have a link to on my slides there is this model. And this repository provides all the necessary tools to perform audio source separation with the SEPformer model implemented with SpeechBrain and pre-trained on the Wall Street Journal corpus of a 2 mix. So 2 people. It's built to separate 2 speakers out of the audio. For a better experience, we encourage you to learn about SpeechBrain. Yep, SpeechBrain's cool. Anyway, I just grabbed this little bit of code and put it into a Google Colab book and notebook. I will point out, I didn't point out, but let me just, you can see here, this is one track. This is not a multi-track thing. This is one track that both of us were speaking into one microphone at the same time on one track. And let's see how it's doing over here in my Colab. Okay, it took 37 seconds to run. And it should have created, let me refresh my file system. Yeah, it should have created, and it did create 2 files, source1 hat.wave and source2 hat.wave right there and there. Let me just download these. And if you just double click, it'll download, and I already did previously, but let me double check. Yeah. So they're sitting on my hard drive. Let me bring my Finder over to this window for us to see together. And if I look for source1 hat, I'll play it. Well, let me get it over here. Ready?
I like to eat apples and bananas. I like to eat alt.
So it did pretty good. You can hear me a bit, in particular, at a particular point in the recording, you can hear me a bit, but let's listen to this one over here. This is me.
My name is Earl Brown, and I teach linguistics at Brigham Young University.
So you can hear it did pretty good, but it got her laugh at the very end there, and it has a little bit of background noise of her speaking. But it did a pretty darn good job. I mean, that's pretty impressive to have a single track with this stuff. You know, my name is Earl Brown. Both of us talking at the same time on the same track, and then pull out these 2 different files that could be then fed into like an ASR system to get better transcription, right? So, that's another application of ASR systems. Not much code. Let me go back real quick. Not much code there. I mean, you just pip install SpeechBrain. This is right at Python. Let's say terminal shell command, right? Just pip install SpeechBrain. And this is Python code. There's not much there. You load in the model right there, pass in the WAV file that you want it to do diarization on, and then the names of the files you want it to save. I will point out that it downgrades to 8,000 hertz. It'll downgrade if the audio is above 8,000 hertz, it'll downgrade it to 8,000 hertz. There. So anyway, that is speech diarization or source separation. Oh, by the way, let me jump back. Sorry. There also is a way to do it with 3 speakers. Let me jump over here. Let's see if I can find it quickly. There's a way to do it with 3 speakers. Let me see if I can find that quickly. If I can't, you'll just have to believe me that you can do it with 3 speakers. They have a model sitting here in Hugging Face. I don't see it quickly here. There's some more speech separation. You can do it with more than just 2 speakers. I just do it with 2 for this demo. Okay, good. So the next lab is to look at one of the tutorials or a couple of the tutorials and look around and see what we can find on these different topics of applying ASR technology to some specific application and to work with one of these applications. And later in the semester, we'll look at more advanced applications of ASR. Okay, so as always, let me know how it goes, and I'm super happy to help. See you next time.